Hey there, welcome back to Short Take 331. Today we're going to talk about the quantum free particle. So finally, a little bit of physics, though not a lot, but a little bit. So today then we're going to talk about this quantum free particle. Let's jump right in. So classically, a free particle is one that is not affected by any external forces. And so by that what we mean is that when we write Newton's second law, F equals dp dt, that's equal to zero. Of course, we had to talk about inertial reference frames and so on. I'm going to put that aside, assuming that you've already seen that in one or several classical mechanics courses. And what this means, of course, is that the momentum is constant, and that's just the mass times the velocity. So the particle is just moving in a straight line, and there's not a lot of interesting stuff going on. In the Hamiltonian formalism, which is what we want towards moving to quantum mechanics, we simply write that the Hamiltonian is p squared over 2m. And this p squared, you have to think that p is a vector, and so it's px squared plus py squared plus pz squared, or however many dimensions you're in. But if you're just in one dimension, then from this Hamiltonian, the equations of motion are just that the time derivative of dh dp is equal to minus dh dq. This typically gives you the forces. The forces are zero, and so once again we have that p is constant. So here I use a vector again, but of course this is in general in 3D, 2D, or in 1D. As you have here, where I sort of implied that p is just one variable, which you can call px if you want. Now, this is the jumping place, basically, to quantum mechanics. So from here, we go ahead and promote the Hamiltonian to a linear operator, and it would take this form. So the Hamiltonian now is a linear operator acting on a vector space of wave functions, a space of states, and the Hamiltonian takes the form p squared over 2m. This is minus h bar squared over 2m times the second derivative operator, because p is promoted as well to an operator. The momentum p is h bar over I times the first derivative operator. And h bar is, of course, Planck's constant divided by 2 pi. Now, the idea in quantum mechanics is that the stable states of a system are given by the eigenvectors of the Hamiltonian. And the idea, once again, on this is that the Hamiltonian generates time translations. And so states that are stable, that don't change with time, must then be eigenvectors of the Hamiltonian, because when you apply the Hamiltonian to them, they don't change. So that's, by definition, what we mean by an eigenvector. It's a vector that defines a kind of stable direction, a kind of invariant subspace in the vector space where you're living, which is a space of states of the system. And so it makes perfect sense that the eigenvectors of H are the states we're after as stable states. And the energy of those states will be the eigenvalues. So it's going to be an eigenvalue given that gives you the energy for each of the eigenvectors. And so we have to solve then our eigenvalue problem, our secular equation, if you want, where we take then minus h bar squared over 2m times the second derivative acting on our function, our wave function, our vector is equal to the energy, so our eigenvalue times the vector once again. So this is a differential equation. We have to solve this differential equation with some boundary conditions, and once we have that, then that boundary condition, those boundary conditions with the differential equation will tell us which values of v are possible. And so for a free particle, for a truly free particle in 1D, then we can it can live in the whole real line. And so then our eigenfunction will take the form psi sub k. There will be a parameter k, which will be the momentum as a function of x is equal to a constant. Remember that eigenvectors are defined up to an overall constant because this equation is a linear equation, and so you can multiply psi by whatever you want as far as it's a constant, and you'll still get a solution. And so on the real line again, then we have the constant times e to the ikx. So this k, as I said, is going to be the momentum, and the energy associated with this wave function, with this state, is h bar squared k squared over 2m. And the only way, or rather the simplest way to solve this problem is to say, well, what function do you know such that you take two derivatives and you get the same function times a constant. And of course, it's sines and cosines and exponentials and so on. And this is one way to write that. You can combine these in different ways. Now, to truly have an eigenfunction of momentum, then you can't really use the sine and the cosine, because if you take a derivative of a sine, you get a cosine. If you take a derivative of cosine, you get a sine. So you really, in this case, need this simple complex exponentials e to the ikx. And so in that case, then you apply the momentum to psi, and you get h bar k times psi. So your state is also an eigenstate of momentum, which is what you would expect, because momentum is also a conserved quantity. And so, by the way, this constant is 1 over 2 pi to the 1/2 in 1D. This is a convention, it's a normalization convention. We could have chosen it to be something else, once again, because eigenvectors simply satisfy this equation. Now, the three-dimensional generalization of the above is involving the Laplacian operator, which is the sum of the derivatives in the x, y, and z directions. And of course, in 2D, you just omit this term and you have the 2D form. The wave function then takes the form of a complex exponential where in the exponent, you can have plus minus I k vector dotted with r. So in the usual sense of dot product, where component by component, you do the multiplication. And then you have h bar squared k squared over 2m, k vector squared over 2m, that's your energy. And so coming with this, you have orthonormality conditions, which I didn't mention before, but which also are true in 1D, which tell you that the integral from minus infinity to infinity of wave functions evaluated at the same point, same argument, but different momenta, are orthogonal. That means that you get 0 unless k is equal to k prime. But if k is equal to k prime, then the complex conjugate that you have here will cancel out your exponential from the other one. You get 1. You're integrating 1 from minus infinity to infinity. That gives you infinity. And it turns out that actually that behaves like a delta. It's not just any random infinity. It turns out that when k goes to k prime in this product, that integral converges to a delta of k minus k prime. And so that's the orthonormality condition that you have. And you also have a completeness condition. And if you have never seen orthonormality and completeness, I refer you to our past few videos where we talked about these issues, these definitions of orthonormality in the context of an inner product. And beyond that, when we talk about basis and complete basis and so on, we talk about completeness. And in this case, completeness is a statement of having the integral from minus infinity to infinity of this wave function evaluated at different arguments, but equal wave number k, vector k, but r and r prime. That gives you a delta of r minus r prime. That's in three-dimensional space. Now in a box, if we define a box, so our space is not now from minus infinity to infinity, but it's a box from 0 to L, then if it's a hard wall box, what we call a hard wall box means that the wave function vanishes outside of 0 here to the left and outside of L to the right. And in that case, we have that our wave function is a sine, actually. It's square root of 2 over L sine of n pi x over L. This is a function that correctly vanishes at 0 and vanishes at L for any number n integer going from 1 to infinity. Remember, we saw in a previous video that n equals 0 is not allowed because then that makes this wave function completely vanish, which then is not a proper eigenvector. And you may want to see if n can be negative. Yeah, it could be negative, but then you don't get anything new because you would just change the constant in front because the sign of something with a minus sign is minus the sign of the argument. So you don't have to worry about the negative ones. They don't give you anything new. Now, the energy associated with the state is a lot like the energies we saw before. There's an h bar squared over 2m, basically giving you the units. And then you have a type of momentum here that appears squared up here. Well, here's n pi over L squared. Now, don't let that trick you. Here, momentum is not a good quantum number. The magnitude of momentum is, but the momentum itself is not. The particle, of course, cannot have conserved momentum because it has to bounce against this wall and bounce against this wall. So in reality, this is not a free particle. This is sort of a trick that I'm playing on you here. It's a standing wave. A standing wave is not a free particle. It bounces back and forth and produces a standing pattern. And so this is not really a standing wave. It's not really a free particle. But you do have a very similar pattern of wave functions as you had before. Clearly, what you have here is a linear combination of waves that go like e to the ikx and e to the minus ikx. So one is going in one direction, the other one is going in the other direction. And when you superimpose those, you obtain your sine of n pi over L times x, which obeys, once again, the right boundary conditions. You might wonder about the cosine of the same argument. Well, that one would not obey the boundary conditions, and so that's why that one gets discarded. We have, as before, orthonormality and completeness conditions. The case of orthonormality is written with an integral from 0 to L of wave function at x index n, wave function at x index n prime. The first one is complex conjugated, and you get delta of n prime, Kronecker delta n prime. Completeness is a lot like before, but now instead of having an integral from 0 to L or from minus L to L or what have you, you actually have a sum, because our states are discrete. By virtue of our boundary conditions, our states are now discretized. This is not something we had before. So up here, in the cases of truly a free particle in the real line, momentum is a continuous variable in 3 dimensions as well. Nothing changes that. What does change that, what imposes a quantization condition for the energy, is the boundary conditions. And so that tells you that the states come indexed by an integer n, actually a natural number n, starting at 1 and going to infinity. And so we have to sum over all of those. So n equals 1 to infinity is our sum. And we get psi n of x prime, the first one complex conjugated again, and that gives you a delta of x minus x prime. And this can again be generalized to 3 dimensions in that case where you have a box that obeys these conditions, but imagine that generalized to a square in 2D or to a cube in 3D. And in that case, what you obtain is a product of wave functions of this form, 1 for x, 1 for y, 1 for z. You get 3 quantum numbers, and the energy is the sum of the 3 energies associated with each mode in each direction. And you have a triple sum, and you have a triple integral, and so on and so forth. That generalization is absolutely straightforward. Finally, something that is close to my heart, I have to mention what happens on the lattice. So now, in a way, we once again don't really have a free particle, but you can imagine that this lattice is an approximation to something that will eventually appear in the continuum limit. And so if you're on such a lattice, then you will have n points, big N points, labeled from 1 to n here, and using the index little n. We can assume we have periodic boundaries. And so once again, the wave functions will take the form of complex exponentials, but now the momentum is going to be, the argument of the exponential is going to take the form 2 pi over n times k, an index that goes from minus n over 2 plus 1 to n over 2. And this is a choice. This can be shifted, but this is what we call the Brillouin zone, the first Brillouin zone. It includes the 0. And then this little n here is, of course, the index on the lattice that gives you the position where you're evaluating this discretized wave function. You're free to arrange all this into a vector with a big N components labeled from 1 to big N, and so you can arrange this into a big vector. And if you see any relationship between this and what we saw before, the discrete Fourier transform, then it's because that's exactly what's in the background there. There are energies associated with this in the same way as before, where now you start to see a first appearance of the lattice spacing determining how that energy is discretized, as well as 2 pi over n. And if you combine this big N squared with this little l squared, then you see the whole length of the lattice, the length of the box, if you want, which you might call big L. And if you do that, then you can identify what we call a quasi-momentum. Again, momentum here is not really a good quantum number. It's a quasi-momentum that we have here because we're not in continuous space. So we can't speak of momentum as corresponding to a continuous symmetry. That would require spatial translation invariance that would give you, by Noether's theorem, a conserved quantity. Well, we don't have that here because this translation in space is not a continuous symmetry. And so we only have a quasi-momentum that is conserved, and it comes in these discrete quantities that go from minus pi over L plus 1 all the way to minus 2 pi over big L, and then the 0 mode, and then 2 pi over L, and then so on all the way to big pi, to pi over little l. So this 2 pi over L over big L is usually what people associate with the infrared cutoff. So it's the smallest momentum chunk that you can discern on such a lattice. You jump from 0 to 2 pi over L, and the highest momentum you can have is pi divided by little l in magnitude. Of course, this is minus pi divided by little l plus 1, and you might argue about this side. You can assume that the little l is small enough that this plus 1 doesn't really affect things, of course. And this is then the quantity that people usually associate with the highest momentum. And now orthogonality and completeness in this case finally take the form of sums. In fact, finite sums from 1 to n, or from minus n over 2 plus 1 to n over 2, once again n elements. And here on the top, evaluated at equal argument but different kk prime. So these different modes are orthogonal, and they sum up to the delta, the Kronecker delta of kk prime. And for completeness, you have a sum over modes at different points, and that gives you a Kronecker delta of n prime on the lattice. And that's about it. That's my quick review, hopefully for future reference, of the quantum free particle, the quantum mechanical free particle. I hope you enjoyed it. If you did, please like and subscribe. If you're looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a message in the comment section below. And I will see you next time.